Please welcome, he really doesn't need any introduction, so I'm just ad-libbing, Mr. Douglas Crockford.
Good evening. Glad to see you all here. Even though I need no introduction, I feel compelled to introduce myself anyway. So, I'm Douglas Crockford of Yahoo. Yeah, this is my Yahoo ID, okay? All right. Yeah, but there's more. So, this is my California driver's license, okay? And this is my United States passport. All right? Okay. Now that you have verified my credentials, you now must believe everything I tell you. And you must obey all of my orders. And when asked, you must reveal all your secrets. I mean, it makes sense because, we've gone through this identification ritual. One other. This is my identity membership card from the Cosmopolitan Hotel in Las Vegas. Las Vegas is one of my most favorite cities, and the Cosmopolitan is my favorite of all hotels. And if anyone from the Cosmopolitan is watching this, you probably want to bump my identity status from silver up to platinum. That'd be a really good idea. So the reason I went through all that is because tonight's topic is really important. Officers, you may lock the doors now. We're going to be talking about security. And security can mean a lot of things. So let me first tell you what we're not going to talk about. It's not going to be about physical security, not about emotional security or national security, whatever that is. It's not going to be about imaginary security like the security theater that we all enjoy at airports. I'm not going to be talking about that tonight. I'm not going to be talking about sort of the anti-security, which is obtained by getting tough on crime or going to war unwisely. I'm going to be talking about the security of distributed applications. And I've been concerned about this problem for much longer than I've been concerned about JavaScript. So I've got a lot to tell you tonight. So it's very often thought that this is a conflict between white hats and black hats. The white hats are good guys who are trying to stop the bad guys who are wearing black hats, who are trying to get into our systems. I think this is a really bad way to think about security. I don't trust this model for a couple of reasons. One is, it turns out a lot of the most famous white hats were once black hats, and there have been some famous black hats who had been white hats, and there are lots of gray hats who seem to be playing both sides. So that means you really have to be suspicious of anybody who claims to be a security expert. You just have to. But it's worse than that. There is a sense of over-specialization, that we can rely on the white hats to take care of all of our security, so we don't have to worry about security at all. As developers, it's just not our job. And that turns out to be really toxic. In my travels, I've seen organizations where project managers would instruct their developers to intentionally violate the company security in order to make a deadline, which is an awful thing to do. But their thinking is that eventually the company's white hats will figure out what they did, and some engineers will have to spend some unpaid overtime in order to fix it. But the manager still gets the win. He still gets credit for having met the deadline, even though he violated the company's security in order to do that. That isn't tolerable. We can't do that. And that's possible because of this over-specialization, that we can delegate all of that security thinking to experts, and we can't do that. Instead, we have to recognize that security is everybody's job. Everybody needs to be working on security. It's something we can't leave to specialists. Now, about the format of tonight's talk, I'm going to be giving you a lot of principles that have to do with security, and each one of them is going to have a purple background, purple for principle. The other convention I'm going to have tonight is that sources of insecurity will be presented in red boxes. So one of the sources of insecurity is that things change. Here's an example. When the World Wide Web was first imagined, it was going to be a simple document delivery system. And the security requirements for a simple document delivery system are pretty minimal. But Over time, it has evolved into an application delivery system. And the web is only interesting today because it has become an application delivery system. An application delivery system has very different security properties and requirements than a document delivery system, and the web still hasn't caught up to that. So the web was, as originally intended, possibly secure, but is not as a result of the changes it's gone through. So it is not unusual for the purpose or use or scope of software to change over its life. Rarely are the security properties of software systems re-examined in the context of new or evolving missions, and this leads to insecure systems. So in thinking about security, it means we have to do the right thing all the time. And that turns out to be surprisingly hard because our intuitions about security of network systems are very often wrong. So just intending to do the right thing is not enough. So I'm going to give you tonight a set of principles. I'm not going to be giving you tricks and hacks because ultimately those don't work. There's no security obtained from tricks. And I've seen very specific talks about how to make your application secure, which give extremely bad advice, which might be effective at the moment that it's given, but sometimes not, but which will age very poorly and actually introduce new security problems when the next iterations happen. So, and also there's such a huge volume of tricks and hacks, there's no way I could deliver them all in an evening, no way you could memorize them all, and there's no way you could keep up to date. It's just too much. But the principles don't change. You know, once you get the principles down, then you can reason about this stuff yourself, and you can do it properly. So that's going to be the focus for tonight. Now, this stuff is hard to reason about because your intuitions are wrong. So when we think about other modes of security, deterrence is often a good thing to do. If we can prevent people from doing things by frightening them or by going after them after they do it, then that's sometimes effective. But in online systems, deterrence is not effective. You can't punish an invisible attacker. You can't punish a bot. You can't punish a script. So there's no form of intimidation which will keep you safe. The only thing that works is prevention. Prevention is the only card we have to play. So we need some historical context so we can start thinking about how to think about security. So we're going to start with this guy. This is Johann Martin Schleyer. He was a 19th century German priest, Roman Catholic priest in the Baden area in Germany. One night, God came to him in a dream and told him to do something. What did he tell him to do? Well, in order to understand what God told him, we have to go back a little bit further. So long time ago, on the plain of Shinar, some of the best architects, material specialists, and builders in the world got together to build a tower to reach all the way to heaven. For some reason, God didn't want them to do that. He was concerned about them all getting together and working together and accomplishing great things. That was not something that he intended. So he came down and confounded our speech, caused everybody on the project to start speaking different languages. And then they all wandered off and started their own countries, apparently, and went off speaking their own languages there. Basically, he created the I-18N problem. We don't know exactly when this happened. It was sometime after Noah got drunk and his robe popped open, but before Lot offered his virgin daughters to the Sodomites. So somewhere in that area is when that happened. So then, many thousands of years later, God appears to Schleyer and says, I changed my mind about that confounded speech thing. I want you to invent a new language which will unify the world. And he did. So he created a new language called Volapük. He published a book about his new language in 1880 in German, and it was a hit. There was a huge amount of activity around Volapük. Someone told him that people who speak English were comfortable with umlauts. And I can tell you that I'm not, which is why I keep mispronouncing the name of the language. Now, he was not the first to invent a new language. If you read the Baroque cycle by Neil Stevenson, you'll remember John Wilkins, who was inventing a philosophical language George Dalgarno in England was doing a similar thing about the same time. Those are real people, and they were inventing a real language, and they were not the first to be inventing new languages, and many people after them invented languages. But Schleier's, for some reason, caught the imagination of Europe, and its growth was explosive. Every 2 weeks or so, there was a new journal being published about Volapük or in Volapük. Every other day, a book was being published about or in Volapük. There were Volapük societies forming all over the world. There were about 30 of them. The estimated number of speakers was between 250,000 and 1 million. And this all happened in a few years, just explosive growth. And the reason for this wasn't because it was such a great language design. It was actually a problematic design. But the people of Europe were tired of war. Europe had been in a constant state of war for centuries, and they were never good wars. They were always war about ambition or the failure of politics, and regular people were getting killed all the time and not benefiting from any of it, and they were tired of it. And they could see that Europe was getting even more militant, and they could see bad things on the horizon. And there was some philosophical belief that languages were part of the root of the problem, because everyone was speaking different languages. It was impossible to unify Europe. And there was not a great sense of cultural pride about languages, because in most cases you were speaking the language of some conqueror from many centuries ago, and the conqueror is gone, but you're still speaking his language. Let's find another language. And a lot of people got behind Volapük and said, this is it. This is the way we can go forward together. So there's a huge amount of excitement, and a lot of it was due to this guy, August Kirchhoffs. He was a Dutch linguist who translated the Volapük books into lots of other languages, went all over Europe lecturing about the language, helping to create a lot of enthusiasm about it. He was rewarded for his efforts by being appointed the director of the International Volapük Institute. So he was responsible for helping to promote the language. Being a linguist and having spent a lot of time trying to teach this language, he found that there were some aspects of the language which were unnecessarily complicated. And he thought that if he could reform the language, if he could simplify it, reduce it to its good parts, if you will, then the language would be a lot easier to teach, a lot easier to learn, a lot easier to adopt, and be more likely that the world would adopt this language. At the third International Volapük conference, which was the first conference held all in Volapük, even the waiters at the conference were speaking Volapük. He presented his idea for these improvements to the language. And many of the delegates of the convention said, this is great. Schleier, on the other hand, said no. God had told him to invent this language, and he wasn't going to let anybody else change it. So he insisted that the convention give him a veto. At that point, the convention forked. Half of it went with Schleier, the other half went with Kirchhoffs, and the movement fell apart. Suddenly, there were cunning linguists all over the place who started saying, hey, it's open season on new ideas. I've got new features I want to add, and they started publishing new features, and the language started splintering all over the place. Other people were saying, well, let's forget this language. Let's start all over with Esperanto. Esperanto was actually a better language design, but it never had anywhere near the reach that Volapük had. And the thing fell apart. Less than a decade after Schleier had published his book, it was done. So, and it left things in a worse state. That was less likely now that there would ever be a universal language. So instead of debabbilization, it resulted in rebabbilization. There are actually more languages when he finished than when he started. And it goes on. There have been lots of artificial languages invented since then. Charles Ogden invented Basic English, was taking English and reducing it to 850 words that would be easy for anybody to learn. The guy who created Simon Templar, the saint, created a language called Paleo-Neo. The guy who created the board game Careers created a language called Loglan. J.R. Tolkien created lots of languages for all these mythic races, then wrote poetry in those languages, and then wrote histories about the people who were making up the poems, and used all of that as material in his epic novel, The Lord of the Rings. Tolkien called his compulsion to design languages a secret vice. And it seems that the compulsion that causes some people to make languages is really similar to the compulsion that makes some people make programming languages. They're the same sort of thing. Any idea what the most popular artificial language is today? Any guesses? Yeah, it's Klingon. It's true. So why did I tell you all of that? Well, it's because I wanted to introduce you to Kirchhoff's. Before he got mixed up with all that Volleybuk thing, he wrote in French a book about military cryptography. It was the first modern book about cryptography. Telegraph was a fairly recent invention at this time, and Kirchhoff was the first to re-examine the requirements of cryptography in a world that had telegraph, which had electronic communication. All previous systems had been based on paper systems, and the properties of an electronic system can be quite different. Kirchhoff's was the first to figure this out. And the principles that he came up with still work. It's an amazing piece of work. One of the things he recommends has become called the Kirchhoff's principle. He said, the design of a system should not require secrecy, and compromise of the system should not inconvenience the correspondence. So what did he mean by that? So here we have Alice and Bob. And Alice and Bob want to exchange a message, but they're afraid that they're going to be spied upon. So they want to use some cryptography so that nobody can find out what they're saying. So they've got a crypto system. Alice will take her message, a plain text, and a key, and put it into a machine which will encrypt the message and produce a ciphertext. She can then transmit the ciphertext to Bob, who will then put it in his decryption machine, which might be identical to the encryption machine, and a key, which is probably the same as Alice's key by previous arrangement. And so that way, nobody else can read the text. The thing that Kirchhoff said, which was amazing, was that there should be no secrets inside of the encryption machine. That you should assume that the enemy is going to find out how the machine works. And having them know how it works does not compromise the security of the system. So prior to that, there had been thinking that you could do something kind of silly in the box, and as long as you could keep the contents of the box secret, it didn't matter. Kirchhoff said, no, you got to do this right so that there can be no secrets in that. Some people have taken it further and said, not only should you assume that the enemy has it, you should go ahead and publish it. Make sure that the enemy has it, because that's the only way you can be confident that you've got the right discipline. So one of the corollaries of that is that there is no security in obscurity. Doing something in which the truth is hard to find is not effective because the enemy can find it. Making it hard to find is not good enough. I still see experts claiming that the best way to build a cryptographic system is still to try to hide as much material as possible to force the bad guys to try to find more stuff, uncover more information in order to break it. And it's wrong. And Kirchhoff showed us it was wrong over a century ago. There are some people today who still haven't figured that out. And it's because that the more secrets you keep, the more secrets you have, the harder they are to keep. And keeping any secrets is hard. So in a cryptographic system, the only thing you want to have secret is the keys. And just that is hard enough. Sometimes when we look at cryptographic systems, people will say, well, we're using a good algorithm and therefore we're unlikely to ever be broken. But there are many other places where you can break a cryptographic protocol and you don't get to choose what part of it the attacker is going to go after. They're going to go after you where you're weakest and not strongest. So let me show you an example of that. There's an encryption algorithm called the one-time pad, which is provable to be unbreakable. You cannot break this. All the computers running to the end of time can never break this code. It's amazing. You are going to break it. But first, let me show you how it works. So there are a couple of rules on the use of the one keypad. The first is that the rule that the key must always be kept secret. This is going to be true of any crypto system. The key must be at least as long as the plain text. So ever how many bits you have in the plain text, the key is the same size. That's a little unusual. That's one of the distinct characteristics about this algorithm. And the ciphertext is obtained by simply exclusive ORing the text with the key. So it's pretty easy. So here's an example of it. So this is my message. This is my plain text. It happens to be a picture in this case. It's the JSON logo. Usually we think about encrypting text, but there's no reason why we can't encrypt pictures. And pictures are easier to demonstrate. So that's my text. This is my key. It's a bunch of random numbers. That's all it is, random pixels. For those of you who grew up with broadcast television, you might remember this. We used to watch a lot of this. And it's random. I took a lot of trouble to create random numbers here, and that turns out to be a surprisingly difficult thing to do, but they're there. So if I now exclusive OR the two things together, I now get the ciphertext. And if I did my job correctly, you cannot see any aspect of the image in that. It's completely hidden inside of the randomness. So it looks like I did it right that time. Okay, there's one more rule. The key must be perfectly random, whatever perfectly random is. That in cryptography, there is a sense of randomness which is much more severe or precise than in other disciplines. So let me demonstrate that. So this is a key that I made with Photoshop. I just used Photoshop's noise filter and made this. And it looks exactly like the other one, right? For you in the back, all you see is gray. You sitting closer, you might see some pixels, but you can't see any pattern in this, right? But it was not a cryptographically secure random number generator. So when I exclusive OR with this one, you can see the image, right? It leaked through. Because the key was not sufficiently random, you just broke the code. You could see what the message was that I was hiding. Okay, you are a cryptanalysis now. The final rule is that a key must never be used more than once. So let me show you what happens if you use a key more than once. So here is another message. This happens to be a picture of me in Istanbul. And you remember this is the same key that I used the first time, right? You recognize the pixels, it's exactly the same. And I'll exclusive more of them together, and good, the image is still hidden. So now I'm going to exclusive OR together the two ciphertexts. This is something that an eavesdropper would have access to. And when I do that, the two keys cancel out, and I can see both messages. Exclusive ORing two messages together gives you no security. And so you've now broken two messages. Congratulations. So cryptography is not security. Cryptography is one of the tools that we use to build secure systems, but simply putting cryptography into a system doesn't guarantee it's secure, that there's a lot of other stuff you have to attend to. But one part of the discipline of being a cryptographer is you have to imagine that at every stage in the development of your protocol, you may be vulnerable to attack, and you have to reason all that stuff out. And that's the kind of intuitions that we need to be developing as well in our applications. So one of the things that cryptographers think about is that there are more people involved in this transaction than just Bob and Alice. For example, there may be Eve, the eavesdropper. Eve might have a packet sniffer, and she's just watching all the traffic going on between Alice and Bob. And by analyzing that traffic and by keeping all the messages, she may be able to figure out stuff about what's going on there and compromise them. Eve is one of the standard characters that's of importance to a cryptographer. Another character is Mallory. Mallory can do man-in-the-middle attacks. So Mallory might be operating a free public Wi-Fi hotspot, and Bob connects to Mallory thinking that he's connecting to Alice. So Alice asks, what's the password? She asks it of Mallory. Mallory asks it of Bob. Bob gives his password to Mallory. Mallory gives it to Alice. Bob asks Mallory, what's my balance? Mallory says to Alice, change my password. And Mallory says, please transmit my account to the Caymans, and then sends a message back to Bob saying everything's great. So that's something cryptographers worry a lot about. Then in my own practice, I developed one more character, who I call Satan. Satan is very powerful and totally malicious and wants to be one of our customers. Now, some people think the way you deal with Satan is with an identity system. We'll figure out who everybody is, and as long as nobody is Satan, then everything's going to be fine. And that turns out not to work. There's no way you can do that. So what you have to do instead is assume somewhere among all of our users and customers is going to be Satan. And if we do our jobs right, Satan can come and interact with us and cannot cause us any harm and cannot cause any harm to any of our other customers or partners. Only if we're that confident have we done a good job. So one of the things we should learn from the cryptographers is that security needs to be factored into every decision. So not only is it our job, we didn't used to think it's our job, but it is, but it's our job all the time. Everything we do has to consider the security of what we're doing. In the development of an application, we might end up making thousands or millions of decisions. All of those decisions must consider the security implications of what we're doing. One of the biggest causes of insecurity is we'll go back and make it secure later. That's really common when architects or developers are building a new operating system or a new stack or a new platform or a new set of services or a new protocol or whatever. They think the hard part is getting the machine to boot or getting the thing to cycle or getting the pixels on the screen or getting the boxes to talk to each other. Making it secure, we'll save that to 2.0. And that's a tragic mistake that is really, really difficult to do and is rarely done. And part of the reason for that is that you can't add security. You can only remove insecurity. So if you published a platform and people have used it in an insecure way, it's difficult to then remove those features because they are inherently insecure and replace them with more reliable features. You just can't do that without causing big breakage. It's not compatible. So, you need to fix it before you release it. Another fallacy is that having survived to this point probably means that we're not going to be hacked. And that doesn't work at all. That as we become more successful, as our business grows, we become bigger targets, and eventually we can expect that they come after us. The impossible is not possible. Maybe that should be called Crockford's principle. I think it's pretty good. So you should not be depending on anything which can't be done in order to make you secure, because it can't be done. But also related to that is the idea that you shouldn't be trying to do things that are not going to be effective. Sometimes there's the idea, well, we can't stop them, but we sure as heck can slow them down. We'll put some speed bumps in the information superhighway, and that'll keep us safe for a little while. That turns out not to work at all. If what you're doing is not effective, then it's ineffective, and you're wasting your time. So putting together these speed bumps, you're using resources that could have been used to do something that was more effective. Don't prohibit what you can't prevent. The corollary is that the bad guys will exploit whatever you cannot prevent. False security is worse than no security. If you know that you have no security, then at least you'll be smart about risk-taking. If you think you are secure and you're not, you're going to make really bad judgments. Also, it turns out that false security has a cost. And by pursuing false security, you're not pursuing better forms of security. Which brings us to the browser platform. The browser is horribly insecure. We're still fixing it. The web is now drinking age, and we are still fixing it later. And HTML5 made it worse instead of better by adding a bunch of powerful new capabilities, but not constraining the ability of bad guys to get at those. So it's made everything worse. Despite that, the web is better than everything else. All other application platforms and application delivery systems are strictly worse than the web. And the reason for that is their blame the victim security model. One thing all those systems have in common that the web does not do is ask questions of the user about what a program should be able to do, and generally ask them in a way that the user cannot answer them correctly. And so all that accomplishes is that when the thing finally goes wrong, you can say, well, it's your fault, you agreed to this. although the user never said, I never agreed to have my identity stolen. But you did agree that it could have access to your file system. You go, yeah. And you did agree that it could have access to the internet. And you go, yeah. Well, there you go. That's identity theft. The web doesn't do that, and that's why the web is better at security than everything else. But there's still a lot that it gets wrong. So the thing that the web got right that everybody else got wrong was, whose interest does the program represent? The browser knows that the program does not represent the user or the owner of the computer. The site is represented by the program. All other systems, going back to Unix and way beyond, all the way to the beginning of time, got that wrong. They think that the program represents the user, and so the program gets all of the user's privileges. But the user may not necessarily intend that the program be able to do anything beyond do the useful thing that the program was obtained for. So the web got some things wrong. What did it get wrong? It turns out there are more interests involved than the users and the sites. There can be third parties and fourth parties, many other parties on the same page. And a malicious party can exploit code conventions to inject malicious code onto the page. And that code gets all of the rights of the site. And this can compromise the site and the user. This is known as the XSS problem. So what can an attacker do if he can get some script onto your page? The attacker can request additional scripts from any server in the world. Once it gets a foothold, and it only needs a tiny amount of code to do that, it can obtain all the additional scripts it wants from the most evil websites in the world. The browser has the same origin policy that limits the ability of a page to interact with other sites, but it in no way limits the ability of an attacker to get more script to run on your page. The attacker can read the document. The attacker can see everything the user can see, and a lot of things the user can't see. It can see hidden fields, comments, cookies, all sorts of stuff which isn't visible on the page. The attacker can make requests of your server, and your server cannot detect that the requests did not originate from your application. Now, you should be using SSL to secure your connections, but if you do, it doesn't help you here because the attacker gets access to your secure connections. You should be authenticating your requests from the browser with a special token, sometimes called a crumb. That doesn't help. The attacker has access to that as well. If your server accepts SQL queries, then the attacker gets direct access to your database. It can do anything that SQL will allow him to do. Now, if your server application is creating SQL queries by concatenating together pieces of material that it gets from the browser, then you probably gave access to the attacker to your database because SQL was optimized for SQL injection attacks. The attacker has control over the display and can request additional information from the user. And the user cannot detect that the request did not originate from your application. The browsers all have anti-phishing Chrome in them now. The problem with it is that the users don't pay any attention to it. If they did, the Chrome would be saying, this is a legit request, go ahead and give it. Because what the browser is looking for is where the HTML came from, not where the script came from. And it's the script that's evil here. The HTML is inert. Some sites, whenever something scary is about to happen, think, okay, let's make sure that the user is still on board, so let's ask for their password again. That doesn't help you in this case because the attacker has control of the screen, so he can go to the user and say, what's your password? And everything tells the user that this is a legitimate request, give it up. In fact, if your site routinely asks the user to give up their password at unlikely times, what you're doing is training the users to give up the password anytime an attacker asks for it. The attacker can then send the information that it obtained by talking to your servers or scraping the page or talking to the user and send it to any server in the world. Again, there's the same origin policy in the browser. It does not limit the ability of the attacker to send this information to the most evil site on the planet. Anybody freaked out yet? This is a problem. This is why we worry about security. The browser does not prevent any of these. and web standards require these weaknesses. If your browser does not expose your site and your users to all of these problems, it is not standards compliant. Okay? There's something deeply wrong in the W3C standards. The consequences of an attack are horrible. There's harm to customers, loss of trust, legal liabilities. There's even been talk about criminal liabilities because of negligence of exposing people to harm. So this general category of attacks is called XSS, which is supposed to stand for cross-site scripting. It's not CSS because that's some other abomination that we'll talk about another time. Some stylists I hear in the audience. One of the problems with this attack, it was identified many years ago by some security white hats, I suppose, and they misunderstood what the attack was about, and so they gave it the wrong name. The problem isn't with cross-site scripting. Cross-site scripting is actually a desirable thing. We call that mashups. The problem is this confusion of interests. But the white hats gave it the wrong name from the beginning, continue to use the wrong name, and they expect you guys to keep up. Doesn't make any sense. So cross-site scripting attacks were invented in 1995. We have made no progress on this problem since then. It's appalling. A mashup is a self-inflicted XSS attack. Mashups are great. It's a way of creating an application of components that come from several independent parties and letting them work together for the user's benefit. But they're not safe as currently practiced in the browser. And it turns out advertising is a mashup, which means advertising is a self-inflicted cross-site scripting attack. Turns out the most reliable, cost-effective method of injecting evil code into a website is to buy an ad. Yeah. So why did this happen? There are a number of causes. First, the web stack is too complicated. There are too many languages. There's HTML, HTTP, the cookie language, URLs are a language, CSS is a language, JavaScript is a language. All of these can be embedded inside of each other. They all have different styling and quoting conventions. And also the browsers are all competing to try to make sense out of badly written code, and that makes it really easy for the attackers to hide stuff inside the code stream. We have template-based web frameworks that are optimized for XSS injection. PHP is a popular example of that. The JavaScript global object, or the window object as it's called in the browsers, gives every script the same set of powerful capabilities, so there's no way a page can defend itself from any other script that happens to get into that page. But then, once again, as bad as it is at security, the browser is still a vast improvement over everything else. I wish that weren't the case, but it is. Even platforms that were developed after the browser seem to have avoided learning any of the lessons that the browser figured out. So this all comes down to confusion of interests. The browser distinguishes between the interests of the user and the site, but didn't anticipate that there could be other interests represented. So within a page, interests are confused. And an ad or a widget or an AJAX library, they all get the same rights as your own script. So you hope, if you're loading jQuery, there's nothing to prevent jQuery from deciding, we're going to go rogue today and start harvesting identities. If you're loading their stuff, it could happen. So JavaScript got close to getting it right. There's a lot that's wrong with JavaScript, but you can avoid most of that. And for the rest of it, we're at ECMA, where we maintain the language, we are slowly making progress in reforming JavaScript into an object capability language with which we can finally write secure applications. HTML, on the other hand, we haven't seen any progress there. It grants power to confusers. It is itself easily confused. It's forgiving because web developers in times past were incompetent, and there was a competition between Netscape and Microsoft to try to capture as many incompetent webmasters as possible. And the DOM's API, or the DOM is just awful. So I don't think the DOM can be repaired. I think ultimately we have to replace it. And we should replace it with something that looks like YUI or jQuery, because we know how it should work, and the way the raw DOM is just awful. So anyway, this stuff is not going to get fixed in a hurry. So it's up to you to create secure applications on an insecure platform. It's hard, but there is hope, and there's hope in principle. And the name of the principle is the principle of least authority, which says that any unit of software should be given just the capabilities it needs to do its work and no more. The problem we have in the browser today is that it gives capabilities to all of the script, but we're getting better at being able to put some constraints on it. The capability model came out of the actor model that was developed by Carl Hewitt and his students at MIT in 1973. The actor model is a brilliant thing which is slowly starting to get recognized as the brilliant thing that it is. It has the potential of solving the multi-core problem and the cloud problem. I mean, there's nothing else that can scale at those two extremes. It's pretty amazing. And it also has a security model that falls out of it. So in the actor model, an actor is a computational entity. It could be an object or a little program or something. It's something that can run somewhere. An actor can send messages to other actors only if it knows their addresses. Every actor has an address. An actor can create new actors, and an actor can receive messages from other actors. So web workers are like actors in that you can create a web worker and give it some work, and it'll send you a message when it's done. That's pretty neat. Web services are not, because the security model is different, but that could be repaired. So there's a system I invite you to look at called Waterken, which applies the actor model to web services. And so you get very easily distributed, reliable services with also a very high level of security. So check out Waterken, it's really neat. So I've been talking about capabilities. The address of an actor is a capability. A reference to an object, like if you have a reference to a JavaScript object or a JavaScript function, that is a capability. So let me tell you more about capabilities, because I think this is the most likely mechanism to allow us to be secure in the browser. So A is an object. A has state and behavior. And object A has a reference to object B. And object A can communicate with object B because it has that reference. Object B provides an interface that constrains access to its state and references. So having a reference to B shouldn't mean that you can get in the middle of B and mess with it. It just means you can get to B's interface. Object A does not have a reference to object C, so object A cannot communicate with C. It's almost like there's a virtual firewall between C. It simply can't get to it because it doesn't have its address. In an object capability system, an object can only communicate with objects it has references to. An object capability system is produced by constraining the ways that references are obtained. A reference cannot be obtained simply by knowing the name of a global variable or a public class. And there are exactly 3 ways to obtain a reference: by creation, by construction, and by introduction. So by creation means that if a function creates an object, it gets a reference to that object. Okay, that's pretty straightforward. By construction means that an object may be endowed by its constructor with references. So as part of its initialization, it can get some stuff, some ability to communicate with things. And then 3, this is the most interesting one, by introduction. So here we have a situation where A has references to B and C, and it would like for B and C to be able to communicate with each other. So it can do that by introducing them. So it sends a message to B, which includes a reference to C. So when that message is delivered, B now has that reference, now has the capability of interacting with C. It has acquired the capability. If references can be obtained by creation, construction, and introduction, then you may have a safe system. Potential weaknesses include arrogation, corruption, confusion, and collusion. Arrogation means to take for yourself without right. Examples of that would be global variables. That's the big problem in JavaScript. In Java, it would be public static variables, and also standard libraries that give you access to powerful capabilities simply by knowing the name of the library. Address generation allows for this, so C++ is not a secure language. Known URLs can also do this. Corruption. It should not be possible to tamper with or circumvent the system or other objects. Confusion. It should be possible to create objects that are not subject to confusion. And fourth, collusion. It must not be possible for two objects to communicate until they are formally introduced. Let's skip that. So ultimately, every object should be given exactly the capabilities it needs to do its work and no more. So capability should be granted on a need-to-do basis. So in good design, you have information hiding. Turns out you also have capability hiding. Intermediate objects or facets can be very lightweight, and class-free languages can be especially effective. So a facet object limits the guest's object's access to a powerful object. So here, the guest object cannot tamper with the facet to get a direct reference to the dangerous object. References are not revocable. So once you give a reference to an object, you can't ask it to revoke it. Actually, you can ask it, but you shouldn't depend on it obeying your request. But you can work around that with one level of indirection. So we can have a guest object that has a reference to an agency object, and the guest asks for an introduction to the powerful object. It gets given a facet, not a direct reference. And at any time, the agency can ask the facet to drop its link, and then it becomes useless. A facet can mark requests so that the powerful object can know where the request came from. It gives us some accountability. So facets are great. They're very expressive. They're easy to construct. In JavaScript, it's just a function. They're very, very cheap. They allow us to attenuate the power of dangerous objects. They give us revocation, notification, delegation. It turns out that the best object-oriented patterns are also capability patterns. So sometimes when you're trying to design a system and you're trying to figure out the interfaces and the APIs, if you look at it from a capability perspective, you usually get the right design. It turns out that good systems are also secure systems. It all depends on functions. Functions in JavaScript become the mechanism by which we can build secure applications. So for more on this, I recommend that you watch the Lazy Programmer's Guide to Secure Computing by Mark Stiegler. When you finish with this, just go to Yahoo and Google for Lazy Programmer's Guide to Secure Computing and watch that. It's a great show. It's about being smart and lazy at the same time and getting secure systems as a consequence of that. So one of the things that makes JavaScript difficult to program securely is that there are hazards in it. So this is an example that Mark Miller produced. We want to build a table object which will have three methods in it called get, store, and append, which all work on a secret array. And the array is encapsulated inside of a closure. This is the object's closure pattern, so that the attacker should not be able to get at array. So array is the thing that we're trying to defend. But it turns out there is an attack which will allow the attacker to get the array out of this object. Anybody see what the attack is? In this case, our array is not a global variable. So no, it's not going to be that. Okay, so here's the attack. I use the table store method to replace the push method with my own function. And that function, when I call it, or when I trick it into calling it by calling its append function, will then put it in and I score. The reason for this is one of the design errors in JavaScript. JavaScript doesn't have real arrays. Its arrays are just a little bit of trickery on top of objects. And so with get and store, we assume that I is going to be a number. But it can be anything. And if it turns out to be the name of a method, we can replace a method. And that's not what we intended. But this is confusion because JavaScript doesn't work the way we think it does. I mean, for our own purposes, we need for arrays to work the way we think arrays should work. But that's not what JavaScript does. So the difference between those two causes confusion. Confusion causes bugs, and in this case, a security hazard. Yeah? Oh, sure, there are lots of things. Like you could put, there are a number of fixes to this. The most obvious would be put a type of I and make sure it's a number. But that's a level of defensive programming that most of us don't anticipate that we need to do. So the fact that the language doesn't match our expectations is what leads us into these sorts of problems. So confusion's a bad thing. Confusion causes bugs. Confusion gets in the way of reliability, also gets in the way of security. Confusion aids the enemy. Bugs are a manifestation of confusion. So with great complexity comes great confusion. So it's hard enough to reason about what our programs do just in terms of their functionality, but now we have a whole nother level of reasoning that we have to do. So in order to have any hope of being able to do that effectively, we need to keep our designs as clean and as simple as we can, because complicated, busy designs are difficult to reason about. So we should code well. It turns out good code is ultimately cheaper to produce than bad code over its whole life cycle, so you might as well just write good code all the time. And good code helps serve the interests of security. Good code is easier to reason about. Code that is difficult to reason about is more likely to be problematic in terms of reliability and security. So strict conformance to good style rules is really important. It's important for reliability, even more important for security. So if you're using JavaScript, you should be using JSLint. It does not guarantee that you're not going to have any security problems, but if your code passes JSLint without warnings, then you know your code's going to be easier to reason about, and you'll have a better time trying to find the big problems. Never trust a machine that's not under your absolute control, and sometimes I'm not even sure about those. So I can trust my server. I know what I put on the server, and I know what it's going to do, but I'm not sure about the services that it's talking to, the things that are out on the other side of my wall. And probably the machine that I'm most worried about is the browser. Never trust the browser. The browser cannot and will not protect your interests. You must properly filter and validate everything that comes from the browser. You must properly encode all output that's going to the browser. Context is everything, so you need to understand where inside of the HTML stack stuff is going to go. Encoding inside of a paragraph is different than inside of a style sheet, is different than inside of URL, different than in an event handler. Wherever you're putting that stuff, you've got to make sure it's encoded properly for its context. Everything has to be filtered and encoded. So let me tell you an example. Okay, a friend of mine was going to fly to Asia, and he had a coach ticket, and he thought, hey, that's a long trip. It'd be nicer to go first class. So he went to the airline's website and tried to upgrade, and they said, well, you need this many upgrade certificates, and you have 0. So he go, oh. So he opened Firefox and found the variable that contained his number of certificates, bumped it up, tried it again, and he flew first class to Asia. And the reason that worked was the server trusted the browser to enforce the policy about how many certificates he needed in order to file the request. Shouldn't do that. You should not trust the browser to be looking after your interest that way, that the server has to validate everything that comes to it. So one of the things that makes the web stack problematic is templating. With templating, it's really easy to echo something into a form and allow for evil content to get injected. So this is one of the simplest possible XSS attacks. You trick a user into somehow following a URL to your site with this goofy-looking file name. And there are a lot of ways to do that. If you can get them onto a page, you can generate this. You could post to an invisible iframe, or you could have a short URL that will translate into this. The user might never know that you're doing the stunt. And a lot of web servers, by default, will generate a 404 page, simply taking that file name and sticking it in a body and sending it back. So the effect of this now is that the script runs with your authority. So that script gets your cookies, gets your local storage, your local database, anything that you can get at on the browser, he has now gotten to. And he's got the Chrome working for him too. You know, everything says it's a legit site. So he can be loading in more stuff really easy. And the fault here was that something which was safe in URL position is not safe in HTML position. So it had to be coded. But one of the problems with PHP and other templating systems is it's much easier to do it wrong than to do it right. So it's on us to do it right. Anytime you're going to be inserting anything into the HTML stream, if there's any chance that it could be harmful stuff, you've got to make sure that it's encoded properly. Just getting it from your database is not evidence that it's safe. Everything has to be properly encoded. There's a similar kind of confusion that can happen when you're concatenating, and this can happen in JavaScript too, but it happens in lots of languages. Like if you should never build a JSON text by concatenation, because the attacker could give you a text to insert into the JSON payload which contains quote marks, and those quote marks will then break the JSON encoding. And if this stuff gets evaled, some people are still using eval for this. They shouldn't, but that still goes on. That can cause an injection of bad code. So when there's a good encoder around, you should always use it. So there are JSON encoders everywhere now. Always use JSON encoders. Don't build stuff by concatenation. Same goes for SQL. Never build SQL strings by concatenation. It's way too easy to create an excess SQL injection attack. One of the causes I used to hear a lot of security is, why would anybody do that? You know, why should I have to defend against these things? It doesn't make sense why anyone would do that. I haven't heard this in a long time now. We've spent enough time on the internet that we know the answer to this. The reason they'll do that is because we let them do that. So if we don't want them to do that, we shouldn't let them do that, and that's that. So in our programs, there can't be any capability leakage. We can't allow irrigation. Everything must be solid. If anything leaks capabilities, then everything can be compromised. If a user has rooted their identity in one of our accounts, and if we leak, the consequences can be tragic. This is especially true for sites that offer any kind of email, like Yahoo or Google or AOL or anybody else, because some users will root their identity in that. So when they forget their bank password, it goes to that account. So if we're giving access to that account to attackers simply by doing any of these XSS tricks, we've done a lot of harm. So we need to be really, really diligent. So I'm at the end. So I've got a few more principles I want to throw at you. Inconvenience is not security. We see a lot of instances where it says, oh, you want to do something routine, huh? What's your root password? You know, that doesn't make any sense. So just because you're making people inconvenienced doesn't mean you're making things any better for them. Identity is not security. I see that mistake a lot too, that if we can just get people's credentials, then we can compel them to do whatever we want. That's probably not a good idea. There's a model of security called tainting, where we try to find the sources of insecurity and track them all the way through the system. It seems nice, but it doesn't work in practice. There's some operators who've gotten so tired of the fact that they're constantly under attack that they've sort of given up. And so we're not going to prevent the attacks anymore. We'll just try to figure out when we are attacked. I can see why they want to do that, but that's not a substitute for security. Knowing that you've been attacked doesn't do you any good. Last slide. The last source of mismanagement, or last source of insecurity is mismanagement. That it should be everybody's job to maintain the security of the site. And so the executive staff has to make sure that they are not creating incentive systems which incent anybody at any time for any reason to violate the site security, because you just can't tolerate that. So you as developers need to know that you're supported all the way up to the top, that everybody agrees about the fundamental importance of getting the security right. And with that, I'm done. Donagos et niet gudik.